Page 83, Chapter 3, Part 2, Chemical Bonds. Chemical bonds are intramolecular forces that hold atoms together in a compound. In English, the word intra means within. That means within or between the atoms. Later in this course, we'll distinguish between intramolecular forces, that is, chemical bonds, and intermolecular forces. Those are forces that hold different molecules together. There are basically two kinds of chemical compounds. In its broadest sense, we can say there are ionic compounds and there are covalent compounds, also called molecular compounds. We'll start by comparing their properties. Ionic compounds are made when metals bond with nonmetals, and they're made of metal cations and non-metal anions. By comparison, a covalent or molecular compound is made when a nonmetal bonds with another nonmetal or with metalloids, and they're made of neutral atoms. Look at the properties of ionic compounds. They're all solids, and they're high melting solids. Melting point is typically greater than 400 degrees Celsius. An example is table salt. The melting point is 801 degrees Celsius. You have to heat that quite a bit to get the molecules to start moving. And calcium sulfate, the plaster that's in drywall, has to be heated to 1460 degrees Celsius to melt it. By comparison, covalent compounds can be gases or liquids or solids, but if they're solids, they're relatively low melting, typically less than 300 degrees Celsius. There are a few exceptions, but most fit this description. For example, the boiling point of water is 100 and the melting point is 0 degrees C, and that's quite a bit lower than that of an ionic compound. Ethanol is a typical organic compound. It melts at minus 114 degrees Celsius. It's a liquid at room temperature. Ionic compounds contain ions, and so they conduct electricity when they're molten or dissolved in water. And many ionic compounds are water-soluble. Covalent compounds contain no ions, so they won't conduct electricity when they're melted or dissolved in water. Some are water-soluble. Let's compare the chemical bonds in ionic compounds and covalent compounds. So ionic bonds hold ionic compounds together, and they are formed by the transfer of electrons from a metal to a nonmetal. Covalent bonds hold molecular compounds together, and they are formed when metals share electrons with other nonmetals or metalloids. So a significant difference here. Metal cations and nonmetal anions form. They become isoelectronic with the nearest noble gas and gain stability, at least in the ideal case. In the case of covalent bonds, no ions are formed, but atoms become isoelectronic with the nearest noble gas, and they gain stability by virtue of sharing rather than taking and giving. For ionic bonds, electrostatic attraction of oppositely charged metal cations and nonmetal anions holds ionic compounds together in strong ionic bonds. For covalent compounds, shared electrons are situated between the nuclei of bonded atoms. So the electrostatic attraction of the negatively charged bonded electrons and the positively charged nuclei hold atoms together in a covalent bond. So it's similar, but definitely different. Now these two classes of compounds are extremes. Many bonds have at least some degree of both ionic and covalent character. Let's skip ahead to page 85. So on the top of the page I have a summary of the properties of ionic compounds versus the properties of covalent compounds, something you should know. Ionic compounds, as we said, are high melting solids, typically greater than 400 degrees C. Many are soluble in polar solvents like water. The rule of thumb is like dissolves like. Water is quite polar, and ionic compounds, well, they're more than polar, they're ionic, and many of them dissolve in water. Most are insoluble in nonpolar solvents like hydrocarbons, like gasoline. Octane is a hydrocarbon, and most ionic compounds are insoluble in such. Molten compounds and aqueous solutions conduct electricity because they contain mobile ions. Let's compare the properties of covalent compounds. We said that they are gases or liquids, and they're solids, but they're typically low-melting solids. Now, carbon is an exception. It's extremely high melting. In fact, it's the highest melting solid of all. If you look on periodic tables or sources, you'll never find the same melting point twice, because if it's 3,500 degrees C, how would you measure its melting point? Anything you put it in would melt before the carbon itself melts. Difficult to do. But as a rule, covalent compounds that are solids are low melting. Now, many covalent compounds are insoluble in polar solvents like water. For example, oil and gasoline float on water. They are insoluble in it. Most covalent compounds are soluble in hydrocarbon solvents and other nonpolar solvents. For example, oil dissolves in gasoline. Liquid and molten solids that are covalent compounds and their aqueous solutions are usually poor conductors or non-conductors of electricity because they do not contain mobile ions. Take a look at page 87, please. Let's compare a molecule of a covalent compound like methane with an ionic compound like sodium chloride. Covalent compounds exist as discrete and separate molecules. You can isolate one molecule of CH4, methane. It's a covalent compound. In ionic compounds, there are no discrete units. Each cation is associated with all the anions around it. Each anion is associated with all the cations around it. It's one continuous three-dimensional crystal. We refer to the minimum combining ratio as the formula unit. In the case of sodium chloride, NaCl, that means there's a 1-to-1 ratio of sodium ion to chloride ion in the crystal lattice. In the case of calcium chloride, we write the formula unit CaCl2. We're just saying there's a ratio of 2 chlorides for every calcium, but we can't really isolate a single unit. They're all joined together in a crystal lattice. Let's look at page 90. Page 90. We're going to draw Lewis structures, also known as line bond structures, to show atoms combining to make molecules. We must start with the Lewis symbols of the atoms. Recall the Lewis symbols of the A group elements show only the outer valence electrons as dots, and the inner shell electrons are not shown because they're not involved in bonding. In the case of hydrogen bonding with another hydrogen atom to form H2, which is the stable form of hydrogen, we see that each hydrogen atom has one unpaired single electron. It would like to have two in the valence shell. Neither one can take an electron from the other, so they simply move together and overlap their valence shell so that each one shares both electrons. We show that by means of arrows. So in chemistry, we have this convention for the movement of electrons. We draw a curved arrow to show the movement of electrons. We use a half arrowhead if one electron is being transferred. And we use a full arrowhead if two electrons are being transferred. Now, in this course, it doesn't really matter at this point, but in organic chemistry it does matter, and we'll use the convention strictly there. I'll just introduce it here as a point of interest. Why not? So we're saying that each of these unpaired electrons from the hydrogens are being shared when the hydrogen atoms move together. Let me color them red. And here they are being shared in a covalent bond. So each line bond represents two shared electrons. It's a covalent bond. In the case of hydrogen chloride, we have two nonmetals, each wanting one more electron to become isoelectronic with the nearest noble gas. Hydrogen would become like helium if it gains an electron. Chlorine would become like argon if it gains an electron. Neither one can take the others, but they can move together and overlap the valence shell so that they share them. Once again, they form a covalent bond. Now notice in the case of chlorine, it had 3 non-bonded pairs of electrons and 1 unpaired electron. After the bond is formed, it still has 3 non-bonded pairs of electrons. Hear me please, you must always show non-bonded pairs of electrons. Anytime you leave them out, you'll lose marks. I'm not just trying to be mean. You'll see later in organic chemistry that every non-bonded pair of electrons is really important. In fact, most of the chemistry, most of the reactions occurs around non-bonded pairs of electrons. We can never forget about them. Notice that hydrogen, which had a dot, does not have a dot after it's bonded. In the case of an ionic bond, when a metal reacts with a non-metal, we're saying that chloride takes the electron from lithium, or you can say lithium donates the electron. You can think of lithium as being a reducing agent and chlorine being an oxidizing agent. It's a transfer of an electron. Now in this case we form a lithium cation. The lithium has no dot, and chloride has filled the valence shell and it owns all the electrons. So often I will draw braces around this just to show that those electrons belong entirely to the chloride. So these are called Lewis structures, and when there's line bonds involved, you can call them line bond structures. Polar covalent bonds. In hydrogen, the 2 covalent bond electrons are shared equally between the hydrogen atoms, and this would be true in any compound made from identical atoms, in nitrogen, in oxygen, in fluorine, and chlorine, and so on. But as you might have already guessed, not all covalent bonded electrons are shared equally. When 2 different atoms share covalent bonded electrons, these electrons are often shared unequally. That is, the electrons are closer to one atom and farther from the other. And although this does not produce ions, they're not ionic bonds, it does produce partial charges. So one atom is slightly positive. We use the term delta plus. Delta is the lowercase Greek letter for D. And the other would be slightly negative, delta negative. And this type of covalent bond is called a polar covalent bond. So in polar covalent bonds, the electron distribution is said to be polarized. Think of the poles on the planet Earth. Think of poles on a magnet. There's a separation of charge. So that is not equally distributed, but closer to one atom. So look at the electron cloud in hydrogen. Looks like a rugby ball. It's equally distributed because each hydrogen atom attracts that pair of electrons equally. But it's unevenly distributed in HCl. So here's the electron cloud in HCl. Notice it's larger around the more electronegative atom because the electrons that are shared spend more time around the more electronegative atom. Sometimes in our structures for polar covalent compounds we draw what's called a dipole arrow, and they look like this. So it's a small arrow pointing in the direction of the more electronegative atom that's taking most of the electron density, with a little positive sign near the end closer to the electropositive atom. Just reminds us that there's no ions present, but there is a small charge separation, and this affects their physical and chemical properties, as you'll see. So how do we determine when a bond is polar covalent or ionic? Would you look at page 93, please? We calculate the difference in electronegativity between the 2 atoms that are bonding, and we compare it to the values in this table. So if you have a metal bonding to a non-metal, use the upper scale. If you have a non-metal bonding to a non-metal, or a metalloid, or 2 metalloids, use the bottom scale. So the difference in electronegativity would tell you the type of bond that's present, and you'll be right most of the time. So for example, say you wanted to calculate the type of bond that's present in HF. We'd say the difference in electronegativity between fluorine and hydrogen in HF. You look these values up in the table of electronegativities. Fluorine is 4.0, hydrogen is 2.1. The difference is 1.9. So this is a non-metal to non-metal bond. We use the lower scale. 1.9 falls in here somewhere. We would say that's a polar covalent bond. On page 95, I have a summary of the process used for drawing Lewis structures, step by step by step. So if you ever need to refer to that, please look there. But we're going to go right ahead and start drawing some Lewis structures. And that would be on page 96. Lewis symbols of ionic compounds. For cations, one electron dot is removed from the valence shell, right here, for each positive charge of the ion. This usually means that all the electron dots are removed, because remember, metals like to empty the valence shell. Only the element symbol remains with a positive charge shown at the top right. For anions, one electron dot is added to the valence shell, like here, chlorine goes to chloride, for each negative charge of the ion. This usually means that the element's valence shell is full, and its symbol is surrounded by 8 electron dots in most cases, or 2 dots for the case of hydrogen gaining an electron. Let's try some examples. I have a worked example here for sodium and oxygen forming sodium oxide, but let's jump right in and go to calcium reacting with fluorine. Calcium is in group 2A, and that means it has 2 valence electrons. And it would like to lose both electrons and form Ca plus 2 ion, releasing 2 electrons. In the case of fluorine, it's in group 7A, which means it has 7 valence electrons. It would like to have 8. So it'll gain 1 electron to fill the valence shell, become isoelectronic with neon, forming fluoride, which will have 8 valence electrons, a charge of -1. So we need 2 fluorines reacting with each calcium. So I'm going to put calcium in the center and fluorine on the outside. Here's our calcium atom, flanked by 2 fluorine atoms. This is an ionic bond. Calcium will donate 1 electron to one fluorine and 1 to the other, and that'll produce this structure, this Lewis structure, Ca plus 2. And here's the fluorides. And we'll put a 2 here. So from that we can determine that the formula would be CaF2. The name is calcium fluoride. Alright, so that's the process. This is the formation of an ionic bond. Now how do we know it's ionic? I just kind of assume that, but let's calculate the difference in electronegativity for a calcium to fluorine bond. Take the more electronegative atom first, subtract the less electronegative atom's electronegativity. This would be 4.0. Calcium is 1.0. The difference is 3.0. Let's check our table and see how that works. Here's our table of electronegativity differences. For a metal to nonmetal bond, calcium to fluorine, the difference is 3.0. That's very ionic. So that bond is classified as an ionic bond. All right, let's try the next page. Page 97. Let's draw the Lewis structures of some more ionic compounds. The reaction between potassium and nitrogen. Potassium and nitrogen. Let's get the electronegativity values and just check the difference in electronegativity to ensure that they are in fact ionic. Potassium 0.9, nitrogen is 3.0. The difference in electronegativity for nitrogen to potassium bond would be equal to 3.0 for nitrogen minus 0.9 for potassium is 2.1. What kind of bond is that? Let's check our table. We're going to use the upper scale, metal to nonmetal. 2.1 falls way up here in the ionic range, so clearly we're saying that's an ionic bond. Potassium is in group 1A. Everything in group 1A has an S1 electron configuration, means it has one electron in its outer valence shell. The Lewis symbol would be K dot. Nitrogen is in group 5A. Everything in group 5A has S2P3 electron configuration. Nitrogen will have 5 valence electrons. Alright, so potassium, being a reactive metal, would like to give up that electron and form a potassium cation and release one negative charge. Notice left side and right side are balanced. They're both 0. Reactive metals like nitrogen would like to gain 3 electrons and form a nitride anion with a full valence shell. So looking at this, we see that we need 3 potassium atoms for every 1 nitrogen atom to form an ionic bond. So let's put nitrogen in the middle, surrounded by 3 potassium atoms. We're saying the bond is ionic, which means that electrons are not shared, they're transferred, and they're always transferred from the metal to the non-metal. So we would have 3 of these potassium cations for every 1 nitride anion, -3. So the formula for this is K3N, and the name is potassium nitride. Okay? Next one's aluminum and chlorine. So aluminum and chlorine, the electronegativities, aluminum is 1.5, chlorine is 3.0. The difference in electronegativity for a chlorine to aluminum bond, 3.0 minus 1.5 is 1.5. What kind of bond is that? Let's check the table. I'm going to use the upper scale. Metal to non-metal 1.5, it just falls in the ionic range, so it's going to be weakly ionic. But that's our classification. So aluminum is in group 3A. All the elements in group 3A have an outer shell valence electron configuration of S2P1. That means it has 3 dots or electrons in its Lewis symbol. And chlorine's in group 7A. All the halogens have an S2P5 electron configuration in the valence shell. So chlorine's going to have 7 dots in its Lewis symbol. Aluminum, being a pretty reactive metal, would like to lose 3 electrons and form an aluminum plus 3 cation and release 3 negative charged electrons. Chlorine, being a reactive nonmetal, would like to gain an electron and form chloride. And now both aluminum and chloride are isoelectronic with the nearest noble gas. In the case of aluminum, it would be neon. In the case of chlorine, or chloride, it would be argon. So we're looking at this and we can say that we'll need 3 chlorines for every 1 aluminum. Let's put aluminum in the center and we'll surround it by 3 chlorines. Okay, so aluminum is the metal. It wants to empty its valence shell by donating to the non-metal. Going to form Al plus 3 and 3 chloride anions, each with a charge of -1. Therefore, the formula is AlCl3, and the name is aluminum chloride. Oxygen and magnesium. Here's magnesium and oxygen. The electronegativities are 1.2 and 3.5. The difference in electronegativity for an oxygen to magnesium bond will be 3.5 minus 1.2 is 2.3, and that's greater than 1.5. Do you recall that was the cutoff for the ionic bonds between metals and nonmetals? That is ionic. Magnesium is in group 2A. Everything in group 2A has an s2 valence shell electron configuration. So here's the Lewis symbol of magnesium. It has 2 dots, or 2 electrons in the valence shell. Oxygen is in group 6A. Everything in group 6A will have 6 electrons in the valence shell. It will be s2p4. Here's oxygen's Lewis symbol. Looking at this, we can see that they should react 1 to 1, because magnesium wants to give up 2 electrons, form an Mg plus 2 cation, and the oxygen would like to gain 2 electrons and form an oxide minus 2 anion. So we can react these 1 magnesium atom with 1 oxygen atom. We're saying that the metal donates electrons to the nonmetal to empty its valence shell to become isoelectronic with the nearest noble gas, which is neon. Oxygen accepts 2 electrons to fill its valence shell to become isoelectronic with the nearest noble gas, which also is neon in this case. That means our Lewis structure of the ionic compound will look like this. So the formula is simply MgO, and the name is magnesium oxide. We have one more to go. Lead reacting with oxygen. Lead and oxygen. Electronegativity values 1.7, 3.5. What's the difference in electronegativity for an oxygen to lead bond? 3.5 minus 1.7 is 1.8. Recall it's greater than or equal to 1.5, so that would be classed as ionic. So lead, as you know, has 2 possible cations it can form. It can be plus 2 or plus 4. In the bottom of this page I specified try it for lead plus 4, and we'll talk about it when we get there. So it's group 4A. Electron configuration of anything in group 4A has 4 electrons in the valence shell. That would be s2p2. Here's a Lewis symbol of a lead atom. 4 dots in the valence shell. Oxygen is in group 6A. Everything in group 6A is s2p4 electron configuration. Everything in group 6A has 6 valence electrons. Lead, if it could lose all 4 electrons, would be Pb plus 4, and here's the 4 electrons lost. Oxygen would like to gain 2 electrons and form an oxide anion. Looking at this, you can see we need the same number of electrons gained and lost. We need 2 oxygens for each lead atom. We'll put lead in the middle, flanked by 2 oxygens. Now, assuming that lead can lose all 4 electrons, which is what we're assuming for this, we'll talk about it in a bit, this would happen, and we'll form Pb plus 4, and then we'll have 2 of these oxide minus 2 anions. So the formula would be PbO2. And the name is lead 4 oxide. Now why did I say lead 4 oxide? Why didn't I say magnesium 2 oxide? Why didn't I say aluminum 3 chloride? Why didn't I say potassium 1 nitride? Do you recall the rules for nomenclature? If the less electronegative atom has only one oxidation state, like in sodium chloride, sodium's always +1, we don't say sodium 1 chloride, we say sodium chloride. We don't say sodium 1 hydroxide, we say sodium hydroxide. So if there's only one oxidation state, for the less electronegative atom, it's not stated. But if there's more than one, we have to state it. Otherwise, it's ambiguous. If you said, I need some lead oxide, the next question would be, well, which lead oxide do you need, lead 2 or lead 4? So it has to be stated when there's more than one oxidation state for the least electronegative atom. Now, I gave some hints here that I really don't think this is ionic, even though Linus Pauling's difference in electronegativity says it is. You understand that this is a quick and simple method of determining it. It's rather amazing that we could so simply determine if a compound is ionic or polar covalent, and it's not going to be perfect, and it isn't. So it works in most cases, but sometimes it doesn't. This is one case. What's a better method? How could I know if this is ionic or polar covalent or whatever? Do you remember at the beginning of this chapter we talked about the properties of ionic compounds? We said that ionic compounds are high melting solids, and they should have a melting point greater than 400. If you check on the web, Wikipedia, some source, you'll find the melting point of lead 4 oxide is only 290 degrees Celsius. Recall that covalent compounds, when they're solids, they typically are low melting, less than 300. This sure looks like a covalent compound to me. However, if you looked up lead 2 oxide, you'd find that its melting point is more like an ionic compound. I believe it's 886, right? Just like sodium chloride. You might be curious, well, why lead 2, not lead 4? We'll talk about that in a later part of this course. So the oxidation state also affects the type of bond. Our delta En calculation is a very good, simple calculation, but it's certainly not perfect. And that's probably a good place to stop for this first lesson on ionic compounds.